All right. Hi, everyone. Thank you all for joining us for another Usalco webinar. These webinars are posted for distribution on Apple Podcasts and our Usalco YouTube channel after this airs today. Our webinar today is about converting to a specialty coagulant specifically for drinking water. And I'll begin by introducing myself. My name is Chris Lacey, and I'm located in the San Antonio area. I've worked in water treatment for 12 years and joined Usalco in 2017 in a technical commercial role. I'm serving now as a technical marketing manager at Usalco, and I've been in this role for almost 2 years. We also have today Brian Leota, who is located in the San Francisco Bay Area. Brian joined Usalco in 2022 and serves as our Director of Marketing and Product Development. He came to Usalco from Brentag's North American water treatment business, where he served there for over 20 years. And finally, our speaker today is Matt Acker, who is located in the Houston metro area. Matt joined Usalco 11 years ago and serves as our Director of Sales for the South. Matt began his water treatment career as a municipal wastewater operator over 15 years ago after completing his BS in biological and agricultural engineering from Texas A&M. And Matt came over to Usalco in 2014 with a focus on drinking water facilities. All right, so for today's event, please email webinar@usalco.com with any questions or requests. This deck will be available for you at the end, and if you need any help finding it after it's posted on the website, please let us know. So for today's agenda, we're going to cover the company profile for Usalco. We're going to get into coagulant chemistry and the purpose of coagulants. We're going to cover the concept of filterability, the concept of injection point optimization, the concept of water sample collection for jar testing. And then we're going to run through a case study that was put together from San Patricio Municipal Water District in Texas. And then we're going to review questions at the end, any questions that have come in. So now I'll go ahead and turn things over to Brian to introduce Usalco for those not already familiar.
Hi, everybody. I'm going to give a brief overview of Usalco for people who don't know about the company. First off, we've got an initiative called Mission Zero, and it's not just a slogan. It's a structured framework that Usalco uses to advance all of our sustainability and operational excellence goals across every facility, every product, and workflow. And we're really committed to these three bold goals of zero accidents, zero incidents, and zero environmental releases. Our Mission Zero framework pretty much guides how we reduce risk, waste, and inefficiencies throughout the company, everything from raw materials to the final delivery of a product at a customer site. And it's a continuous development loop that we've evolved, and it drives environmental safety and operational goals across the company and our supply chain. As far as our mission, our vision, mission, and values, our vision at Usalco is to lead in creating water treatment solutions that not only meet today's needs, but also drive a more sustainable future for generations to come. And our mission is that we're committed to being a force for good in the world, enriching the lives of our stakeholders and communities by addressing America's pressing need for clean and accessible water, and Canada's as well, North America's pressing need for clean and accessible water. And our core values are safety, integrity, customer focus, teamwork, and innovation. And these values guide us in everything we do. We strive for results and ensure respect for people in every interaction. As far as our footprint in the world, we have over 27 plant sites and 7 logistic hubs. So we're truly nationwide, we're coast to coast. We have a team of over 500 people that contribute to positively impacting over 130 million lives in North America and ensuring over 70,000 deliveries annually. We're currently expanding in Southern California, demonstrating our ongoing commitment to growth and serving new regions with advanced technologies. And as you can see on the map here, we've got a diverse location footprint, including specialty and conventional plants, rail hubs, warehouses, labs. It all highlights our operational capacity to meet water treatment needs across the country. This illustration shows the critical aspects of a typical drinking water facility. coagulation, filtration, pH control, disinfection, chemical process control, and operating personnel, all essential to providing clean water. So Usalco offers an industry-leading coagulant portfolio and services that improve filter performance. We can automate coagulant dosing, which is our co-pilot system, and we can provide expert support and training on-site and off-site, such as the Usalco Coagulant Academy, for example. So all of these offerings strive to maximize facility production, reduce maintenance and energy costs, lower sludge disposal and pH control expenses, and minimize carbon emissions, ultimately enhancing the resiliency and efficiency of the entire process. As far as our product line goes, we have a pretty diverse range of advanced coagulants and polymers, all tailored to optimize water treatment processes. And you're probably familiar with our signature brands like Delpac, UltraPac, GPac, DeltaFloc, and UltraFloc. They all provide specialized solutions for various water treatment needs. For iron and aluminum specifically, we have a pretty comprehensive range, including packs and ferric sulfates and ferric chlorides, all designed to enhance coagulation. Our polymers like Polydadmax and EPIs offer additional tools to support efficient coagulation and liquid solid separation. Just a general comment about the product line. It's infinitely customizable. And we take that approach to water treatment. We recognize that every water system out there in the world has attributes that make it unique. And so ours is not a one-size-fits-all approach. We take a technical consultative view on each and every opportunity. Now I'm going to turn things back over to Matt.
Thanks, Brian, and thanks again, everyone, for joining. So getting into coagulant chemistry, what is coagulation? So we're neutralizing the negatively charged particles in the water with positively charged coagulant. And we're looking to reduce the charge of the DDL, or the diffuse double layer, which then reduces the energy barrier. And that energy barrier is what we're trying to penetrate. So this process forms positive ions, to lower the surface charge and destabilize them from reducing the repulsiveness of that double layer. So basicity, basicity is a substitution of hydroxides on the aluminum. There's a wide range of basicities. We look at it on a horizontal scale. So on the left side, looking at aluminum sulfate, ACS, some of our commodities with 0% basicity, all the way up to aluminum chlorohydrate, including some polyaluminum chlorides at 83%. So as we move further to the right, it consumes less alkalinity to really start that reaction or to react with those negatively charged particles. The two pictures of the molecules on the right, very complex molecules, very similar to polymers. So the coagulants create this polymeric, nature, and that's where it's so reactive that it needs less alkalinity to start that reaction. So with that, higher basicity, consuming less alkalinity, in result, you need less pH adjustment chemistry. So, with alum, ACS, you use a lot of lime or caustic. As you move to the right of the scale, there's a lot less of that needed to, increase that pH alkalinity back up to what it needs to be in the system. So purpose of optimization, how do we effectively choose the right product? We discover the most efficient coagulant for that application. Is it iron? Is it aluminum? Rarely, we're using, or I guess iron's more on the industrial side, but, or a combination of both iron and aluminum salts. Find the product that maximizes the metal feed. We're looking for the best basicity for that water. The combination of the three is where the product is at. And if you're wondering about how does price factor into that, it'd be included in that maximum metal content. So when working through the initial product discovery phase of the coagulants, if we're looking for, commodity to a specialty product, looking across the basicity spectrum to compare all products. It's important to consider the products, across all basicities, because raw water organics, alkalinity types, they vary between different water sources. So testing all the basicities, all the different metal contents, again, finding that right ratio for the best optimized performance, looking for that metal to basicity ratio. Here we see a picture of one of our sample kits, where we've got some core products, some additional components, and we're looking to tweak those products, mix and match, really find that specific product for the specific facility. It's not a one size fits all. It really is specialty. So getting into filterability, what is filterability? And we're determining the filterability. It's a scientific way of comparing coagulant performance, through an identical set of filters to contrast coagulants. We use this equipment, shown here in the pictures, with 0.45 micron filters to test the filter turbidity and filter run times. Might have great settling in your basins and your clarifiers, but there's too many fines that are passing through the filters, and that could be from being undercharged, overcharged. So this really helps determine, what that optimal product is. So getting into injection points, at the facilities and the sampling points for jar testing or bench testing. Here we have a drinking water process. For this case, it's a lake. It could have reservoirs, rivers, whatever your water source is. Spreading the products out. Do we add to the beginning of the flash mix, the end of the flash mix? Looking at the rapid mixes. Looking at that order of addition can really change the performance substantially throughout the facility. So when we look at injection points and really what's optimal, we want to try to reduce chemical interference. So in this case, if you take, where the ammonia is injected, right? So you've got chloramines or chlorine, ozone, different types of oxidizers, really focused on getting a lot of those precursors, then ultimately help with, DBPs and THMs in the system. So here, for example, Delpac option 1, being fed in the flash mix after your oxidation. So giving your oxidizer to do what it needs to do and allowing your coagulant to do what it needs to do. And then you've got Delpac option 2, where it's fed right there with the oxidizer. So in this case, it's not great. If you're feeding the products at the same place, your oxidizer is going to precipitate your metals. So now you've lost a little bit of, effectiveness of your coagulant to do what it needs to do. And then at the same time, you're consuming oxidizer, which is precipitating the metals. So you're kind of fighting yourself. For example, we've helped several facilities out where just by moving or separating those injection points, not only got them back in compliance with, DBPs or THMs in the system, but also lowered their chemical dosages, which then ultimately reduce their chemical cost. So allowing the oxidizer to do what it needs to do and then injecting your coagulant is really effective. Ultimately, you would like 50 feet, give it detention time, but if we can at least get 10 feet separation, that still is better than on top of each other. So think about this for a second. Where would you pull your sample from to jar test at your facility, or looking at this example above? So ultimately, when we're looking at coagulation itself, we want everything right before coagulation. So in this case, the best place to pull the sample would be right after oxidation and right before coagulant injection. So maybe right there at the entrance of your flash mix, possibly where your coagulant is being injected. And additionally, if there's any chemistries active ahead of the coagulant injection point, they must be included in that water sample, right? So we want to get those precursors to find what that optimal product is going to be in the plant itself. If you don't have that option, if you currently have your all your products injected in one spot, grabbing prior to, if possible, being able to add bleach or chlorine or some sort of chloramines to get those precursors prior to that the coagulation portion of that jar test procedure. Not having that can give you false positives. Coagulant might look good, but each oxidizer is going to affect your coagulant differently and affect different coagulants differently in this case. The age of the water sample that you pull is also very important. It's very common, to see completely different results if water has been sitting for 30 plus minutes, after being pulled. The thing is the temperature changes, the pH changes, the longer and longer it waits, as well as if you have those oxidizers in there, it's allowing more time to get rid of those precursors. And so that will give you false positives when you're looking at your coagulation. So, especially in the bench testing side, it's just being consistent. We'd like to get everything set up with the jar test prior to testing, and then we go pull our sample and immediately run to get our results. But as long as you're consistently, whether it's 0 minutes, 10 minutes, or 20 minutes, consistently testing at the same time, then your results, should show you the correct trend needed. We actually ran a study where we had the sample sit for 2 hours, 1 hour, 30 minutes, and pulled immediately. And every single time, the water that sat for 2 hours had significantly better results, and had a different product that was optimal for that water. And that again goes back to the longer it sits, the more precursors are removed, your pH changes, temperature changes, and everything else. So super important to grab your water and immediately run test on it. So getting to the case study, as Chris mentioned, this is San Patricio Municipal Water District down in Ingleside, Texas. They actually called because they were having to replace this section of pipe because the amount of caustic that they were having to feed with their water. So every year they would have to cut this section out, remove the precipitation, put a new line in or reinstall that same line. They tried things from impellers to get better mixing, different injection coils, but still had issues with plugging, from all that precipitation on the caustic. So during our discovery phase, we look at 5 main things, is really what determines a successful test. One, we definitely want to try to meet the current program. So that's to finding the mixed energies, the G values, detention times, in really looking at the right product. Again, going back to the basicity scale, trying different basicities, different metal contents, and what is that right ratio. So yes, of the 5 things, we look at pH adjustment chemistry. So how can we reduce that, or, reduce the amount of alkalinity being consumed? So that was the main goal. But there's 4 other things that we want to look at, which is, can we meet or beat the settle water turbidities, meet or beat our sludge generation, meet or beat required organic removal, and then saving the plant facility money. How can we reduce the cost per million gallons? So here's a jar test, from this facility, where jar 1 is your aluminum sulfate. That was the current product that they were using. And then jars 2 through 6 were variations of different polyaluminum chlorides. This was several visits into, so we had kind of narrowed it down to several different products, starting from, our core 30. Here, looking at the picture, some might say jar 6 looks fantastic, and that's what I would go with. Some say jar 2, it doesn't look great. Well, jar 2 actually got the best organics removal, but we lacked in pH adjustment or alkalinity reduction, as well as obviously sludge production, but settle water turbidity. So in this case, jar 5, our Ultrafloc 3218, was the best optimal from those 5 things that I mentioned. Settle water turbidity, organics, sludge, etc. So these are some jar test results. When we look at the red line, which was the alum settle water turbidity, versus the blue line, which was the Ultrafloc 3218 or the polyaluminum chloride settle water turbidity, you can see that reduction of 55. Well, the settle water turbidity, we were able to reduce it for about 50%, and this was actually done by reducing the coagulant dose by 55%. And actually even reducing the metal salts or sludge, generation by 15%. So a pretty significant difference here, right off the bat. And then get into caustic, which was, their main concern. This was calculated during our jar test procedure. We know how much alkalinity is consumed per ppm of the different coagulants. And then we know for every dry part of caustic, it increases the alkalinity by 1.24 milligrams per liter. So with the alkalinity consumption, with the calculation of caustic, we kind of predicted, or calculated that we'd be able to reduce caustic feed by 60%. So this is actually during a full-scale trial. We had the great opportunity to actually run side-by-side aluminum sulfate, which was the current program at the time, and then our polyaluminum chloride. So this picture shows, kind of those settling rates, how it settles in the basin, kind of what we saw in the jars. So on the left, you can see alum really didn't start settling until about halfway through the said basin, whereas the pack, you're talking about a third or quarter, the way in, it's already settling. And with this in return, we got a lot better settling rates or settled turbidities, as seen in the jar tests. Another neat thing about this is this facility is not set up for automatic blowdowns. So with the alum, about every 2 months, they would have to take that basin down and literally have operations rinse and clean these basins. So about every 2 months, and it would take over a shift. So at this point, we're paying overtime, operational overtime, to clean these basins. With the pack, or polyaluminum chloride, in this case, now we reduce the amount of metal salts generated, and the way that the pack settles versus the alum. Operations is now they take it out of service about every quarter now, and it takes them less than a shift. So right there, we've saved some operational costs, which we weren't able to capture in the jar testing or in the jar tests. So from the trial results, similar to what we saw in our bench testing, we were able to reduce the caustic within 24 hours. We reduced our settled water turbidities. We lowered their coagulant dose. We exceeded their TOC removal requirements, and we lowered their total treatment cost per million gallons. So, kind of those 5 things that we really look at to optimize. So here's a picture of, or a graph of the organics removal. So we can see from the blue line is just water pulled from the said basin prior to filter. And we can see what we got there. And then our green is our percent removal. So in these cases, we met the TOC requirements for this facility those days with the specific water characteristics. And what was unique and what we did here is we actually increased and decreased the flow of this plant, of this basin, as well as increase and decrease the dose of the polyaluminum chloride to really see what we would see in high flow rates. Can the product handle the higher flow rates in summer months? The lower flow rates with a lower dosage. What is that optimal? And that's what we're looking for, as we saw in our jar test, as well as what we wanted to try to prove in the full-scale trial. So then this is real data from the trial. As we can see, we were able to, as we as I mentioned in the jar test, reduce the coagulant feed by 55%. 55%. And then even the settled water turbidities, as you can see, left side of the graph, the top left side of the graph, very uneven, kind of scattered settled water turbidities, where we're much more even now and lowered the settled water turbidities by about 50%. And then as far as the caustic usage, as we calculated, we were able to reduce caustic dose by about 50% with the pH or alkalinity of the water that had come in when we started this trial, as well as, you can see the settled water pH prior to caustic injection was much, much higher. And again, that goes back to that higher basicity coagulants, obviously, which consumes less alkalinity. So all in all, after the trial, this plant is fully operational and has been running with PAC for several years now. Still today, we've reduced caustic feed by 60%, reduced settled water turbidities. We're able to reduce their coagulant feed by 55%. So not only on the caustic, we reduced dose, but on the coagulant reduced dose. So now, I can't remember the exact number, but close to 100 trucks less coming in and out of the facility total, and as well as this helps with carbon footprint, within the city. We also reduced metal salts, which, as mentioned, this helps out with their settling and taking the basins down. reduce their operational costs there. And we were meeting and exceeding, EPA required TOC results. And most importantly to them, we saved them a couple $100,000 annually just by switching from commodity to a specialty. Ryan, I'll turn it back over to you.
Right. Thanks, Matt. All right, so let's open it up for questions. I think that you guys have been emailing questions to webinar@usalco.com, and we received a few here. Let me organize this a little bit here. Okay, this is for Matt or Chris, whoever knows the answer. Do you use UV 254 to determine organics removal when bench testing, or TOCs only?
No, that's a great question. We actually use both. So, the benefit of the UV 254, it's a very quick test. And so we can get quick results when we're in the lab, bench testing and things like that. Also, it shows that shows more of the insoluble organics to see what the coagulant is doing on that side of things. Excuse me. And then the TOC, much longer test, we ship those off to our lab to get those results. But that will kind of fully determine, as we grab the TOC and DOC to really see fully what the plant would see when they, switch over to a specialty product.
Yeah, and I'll add for the 254, that particular wavelength is really great at indicating what portion of the TOCs are most likely to create or generate those DBPs in the future. So it's a great, just real quick test that you can do when you're comparing products.
Thanks, guys. And then see this other question. I currently use carrier water for my aluminum sulfate. Can I do the same for polyaluminum chloride?
Yeah, no, that's good and interesting. We feed and highly recommend feeding all of our products neat. Even in jar testing, actually, even aluminum sulfate, we feed neat. And the reason is, with polyaluminum chloride ACH, as mentioned, the very polyremic, molecule, it's very reactive, instantly. So any carrier water, even distilled water, it's going to start looking for that alkalinity to start that reaction. So by the time you use carrier water and it goes into, into the injection point, we've already consumed some of that charge or that reaction. And so you sometimes get false positives. So highly recommend no carrier water.
And let's see, somebody wants to know, actually a few people have asked, where can I get this presentation?
I can help out with that one. So we host the webinar video from YouTube on our website under webinars. So if you go to resources, we have a webinar section, and all of our webinars are listed there. And with the video, we have the link to the PDF, which is this deck. And so that'll be there. Also, if you email us now, we can send the PDF over to you right away, webinar@usalco.com.
Good deal. And then also a few people have asked how to get a sample kit.
I can answer that. So a sample kit. So yeah, we had a picture of a sample kit, didn't we? So our sample kits are something that Usalco technical resources use out in the field. We also have a lot of strategic partners out prospecting and testing our products and across all different types of applications, and so they have access to our sample kits. Now, for direct users, like let's say that you're a municipality and you're interested in trying to optimize your coagulant and you want to run samples, we can help you with that. Just send us an email. Let us know. We'll ask you some questions about your water source, and then we can put together your own kit basically that you can run. So we can send you a lot of different samples, and you can run the different basicities and try to optimize those yourself. We'll help you out with that.
Thanks, Chris. Here's one. This is a good one. This is pretty provocative. So the question is, if transitioning from alum to a specialty coagulant, if that improves plant optimization, but requires capital changes or operator retraining, how do you justify the switch?
Yeah, that's a good question. So when we, as mentioned, especially with this case study, typically when we're going from specialty or commodity to specialty, the savings is in your pH adjustment chemistry. And also, as mentioned, there's operational cost savings as well. So when we look at a total package, and big reduction in the cost per million gallons. So annually, I think that justifies that capital or makes up for that capital needed for any type of changes or improvements to the plant.
Okay, thanks, Matt. And looks like this is the last question.
We do have some chat. We have some chat questions as well, Brian. Go ahead, and then we'll get to the chat.
Yeah. This one: Have you had problems with pack settling too fast?
Not in the facilities, so that's why we do such an extensive bench testing, to really find that optimal product. So as you saw in one that in the jar test picture, jar 6, it was settling too fast. So we knew we didn't need that, right? So you react too fast, it settles too fast, you leave a lot of fines, you don't capture all the organics. So you might have some pass through or plugging with the filters, lacking organic removal. So that's really what we're doing in the bench testing to really prevent that from happening in the plant.
All right. Thanks, Matt. And then do you have sulfate to chloride ratio before and after the coagulant change?
Yeah, we certainly do. I know that's a big topic, and so we certainly before and after collect those sulfide to chloride ratios. The thing is, and I see that the next question as well, as far as the Packle versus sulfate comparison. We've had sulfated packs, and so there's not a lot of chlorides that are added to the water when we're converting. In certain areas, certain areas requires different. Again, this goes back to finding what that optimal product is. With different situations. Whether it's the water or whether what the requirements are. So we certainly look at this and capture that type of data in considering when we're looking at the different optimized products.
Yeah, the other question. Yeah, go ahead.
I just wanted to add to that. And so for the raw water alkalinity coming in, so there's incoming chlorides and sulfates, right, depending on the water source. And so you want to think of those as like a buffer. And so if the coagulant's changing and they have a lot of alkalinity coming in, the overall ratio may barely change at all. So it's going to depend a lot on that incoming alkalinity and what that alkalinity consists of. So with the CSMR, we actually have a tool on our website under tech resources, and then I think it's technical resources. It's called the water balance calculator. And there you can calculate the CSMR after you have your raw chlorides and sulfates coming in, and you can ask us for what the chlorides and sulfates would be for different products if they're not already listed on the sheet. We have a few conventional products listed, but we don't have them all. That's a great question.
Yeah, and I think that wraps up all the questions that we have. So I'm going to throw the mic back.
Sorry to interrupt, Brian. Just, I guess, additional comment there for one of the questions, talking about cold water and pin flock. That's actually a really good question. And what a lot of plants see is, or I guess all of the data that we have and all the conversions, is that polyaluminum chloride was actually designed for cold water. So when you're talking about aluminum sulfate versus the polyaluminum chloride, it's a great transition and specialty product to use for those cold water situations.
Yeah, it's amazing. We have massive applications in Canada and all the way down to the Gulf Coast of Texas, where it's usually very warm and there's a lot of organics. So it's initially, like Matt said, it was created in the Northeast of the United States. So, and then I'll go ahead and close this out. So I really appreciate y'all joining us today. And if you'd like to share this with anyone, we'll be posting it on our website, and it's also on our YouTube channel. So if you have a minute, feel free to subscribe to that. And we also have an Apple Podcast channel where you can listen to our webinars, and those are posted there as well. And we really appreciate it. Thank you all.
Thanks, everyone.
Yep. Thanks, everyone.